All right, so this is lecture 2 on relations. So relations are basically a generalization of functions. We'll talk about how much of the constructions you're familiar with for functions also make sense for relations. Graph, composite, inverse, we'll also see how relations allow us to generalize the notion of equality or inequality, and perhaps most importantly, how equivalence relations give us the notion of equivalence classes and correspondingly a natural partition of a given set into disjoint sets. These are all things we'll talk about in this lecture. So let's get to the definition. So A and B be sets, we say R is a relation from A to B if R is a subset of A cross B. that's very very generous. I mean, like, so many different things can be subsets of A cross B. So I mean, this notion of a relation is incredibly flexible. So anyway, notation, we say X is related to Y if X comma Y is an element of the relation. If X and Y are X comma Y is not in the relation, then we say X is not related to Y, and we write what I wrote in green there, like that, X R slash Y. We'll say X is the input, Y is the output when X is related to Y. The domain is the set of inputs, the range is a set of outputs, and if both A and B are equal, then we can call that a relation on the set A. So notice already that there's no stipulation that one input goes to one output, and so that means that this is a more general idea than a function. So I have some silly examples I'll share with you. My first silly example, let S be the set of all living creatures on Earth. We can say that X's are related to Y if both X and Y are people. I'm making that the definition of my relation. All right. So in that sense, I am R related to Trump. In contrast, I am not R related to Napoleon because he's dead. I'm also not R related to my mom's dogs. They may be treated like humans, but the fact remains that they are in fact dogs. So I'm not related to them according to this relation. Another silly example, unrelated relation. So let S be the set of all living creatures on Earth. Then we say that X is not related to Y if X is not the direct descendant of Y. So in this sense, I am not related to Trump. In contrast, my daughter is not and are related to me since she is my direct descendant. So we can play these kinds of silly word games, but we can also visualize a relation in terms of its graph by directly graphing the Cartesian product, the subset of the Cartesian product which forms the relation. For example, circle here, X comma Y such X squared plus Y squared equals to 1. So this is a relation from R to R, right? I actually didn't say. It's important to say what it's a subset of, otherwise you don't know what the relation is. So I guess I'm declaring here that this is a subset of R cross R. So we could look at this as a relation on R. But I cannot say that. Why is this not a relation on R? This is not a relation on R, because if it's a relation on R, it must have domain R. This does not have domain R. This has domain -1 to 1. So it's not a relation on R, but it is a relation from R to R. And my apologies, my multiple uses of R. This is the real number R. This is just the relation R. There really shouldn't be a confusion, but I know it sounds the same as I'm talking about it. My apologies. Maybe I should make the graphing relation like a pirate R, like R, and stick with real numbers just being R. I'll try that for a little bit. I'll get tired of it, but define R as X comma Y such that X squared plus Y squared less than or equal to 1. This is a relation from R to R. Again, it's not a relation on R because the domain of this is also -1 to 1. So I graphed all the points which are in the relation by shading here. So let's see here, just to talk about it, like if the input is -1, what's the output? The output's just 0, right? If the input's 1, the output's just 0. But like anywhere in between, for example 1.5, it's ridiculous in some sense. Like from the viewpoint of functions, it's ridiculous, right? So like here, if you look at the input being, let's see, I guess it's about what is that? About -0.6 maybe. So if you look at the input, excuse me, being, oh, I need to get some candy or something. Anyway, if the input is -0.6, all those points, all those y values are the output. It's got an infinity of outputs when we input -0.6. Those are all outputs, all right? So that's far from passing the vertical line test, right? Far, far from it. So it's not going to be a function. Excuse me. We talk more about functions carefully in our next lecture. But since a function is a specialization of a relation, we start with relations. Another example, positive lattice. These green dots here, like 1, 1, and so forth. So notice here, if we look at the input of 1, what are the outputs? 1, 2, 3, 4, 5, 6, and so forth and so on. Like if the input is 1, the output is the natural numbers. If the input is 2, the output is the natural numbers. In fact, the output of every input here that's allowed is just the whole set of natural numbers. So again, as I said, this is not a relation on R, since the domain of R is n. Now, if you wanted to make this, well, yeah, I'll shut up. Let me move on here. So integer coordinate grid, there's two pieces, the green piece and the red piece, the green lines, the red lines. So this is kind of funny. If the input is a integer, the output is the whole real line, the way it's set up. If the input is not an integer, like if it's, for example, pi, I'll do e. I can fit e into this graph here. This is about where e is, right? Oh, curses. I was trying to make that x equals to e, but I've drawn too many points because the only thing that are outputted are this guy, and this guy, right? So for non-integer inputs, you just get the set of integers as the output, the way this is set up. Excuse me. So anyway, another silly example, you could say x and y are related if they're rational numbers. So this is a relation from R to R again. I suppose that you could view this as a relation on, well, anyway, that's the natural, from R to R. So like 3/4 is related to 13/730 seconds. Pi is not related to anything since pi is irrational. So what this means is that points in the xy plane with x-coordinate pi will not be included in the graph, but points with close by rational approximations to pi will be included in the graph. So if you were to graph this thing, it would just look like the whole plane, but it's technically got lots and lots of holes, infinitely close to any point you pick. This is a consequence, of course, of the fact that there are infinitely many irrational numbers between any two distinct rational numbers. So we'll talk more about that as we go on in this course. Let us move on here. Composite relations. So what can we say about composite relations? What is the definition of a composite relation? So if we have a relation from A to B and another one from B to C, then we can compose the relations and say AC is in the composite relation if there exists a B such that A and B is in the inside relation and B is comma C is in the outside relation, right? So they match up at B and by definition sends A to C. So this is really just the definition of composite that you saw before, and for functions, it's just rewritten in our current notation, honestly. Here's an example of one. So if I have this relation and that relation, the inputs are odd numbers from 1 to 7, the outputs are even numbers from 2 to 8, and let's see here. So I take R as a relation from A to B, I think. So like R goes 1 to 2, 3 to 4, 5 to 6, 7 to 8, whereas the S is 2 to 1, 4 to 3, 5 to 4, and 7 to 6. So this is a relation from B to A because its inputs are, from B to 2, 4, 6, 8. Ooh, I think there's a typo there. If S is a relation from B to A, then the first thing should be 2 fourths. Like this is not quite right as it stands. I'm sorry, guys. So I think what we want actually is S equals 2. I think the first two are okay, 2, 1, 4, 3. But what we want is then 6, 5, and 8, 7. Then S is going to be a subset of B cross A, which is what we want for S to be a relation from B to A, right? And that's what we'd like because we want to go from A to B to A. Now, that may just be that isolated typo. Let's see. I claim that S composed with R is 1 to 1, 3 to 3, 5 to 5, 7 to 7. So let's see here. Of course, like to see the 1 to 1, to see that 1 maps to 1, that's because we've got like 1 to 2 and then 2 to 1. The 1 to 2 is from the R, and the 2 to 1 is from the S. Let's see here. You have to forgive me. Once I get something flipped around in my head, it takes me a while to unflip it. Let's see here. R goes from A to B. S goes from B to A. Okay. Yeah, let's see here. S. Well. Okay, that's fine. Never mind me. So when we work it out, though, we'll get 1 goes to 1, like we see here. 3 goes to, it's you notice this? S composed with R versus the order R and S. Just got to be careful. This will happen. The order of the letters is reversed from here to here as we read it. Okay, anyway, moving on here. So, in fact, what we have then is that S composed with R is really the relation which takes 1 to 1, 3 to 3, 5 to 5, 7 to 7. This has a name. It's the identity relation on A. And if you look at the other one, R composed with S, you'll get 2 to 2. Now R to S, S goes first, S goes from B to A. So like, let me write out this here. Let me write out here. So like R composed with S, R composed with S is something like S goes from B to A. and then R goes from A to B. So this is just like the pictures we draw for functions. We'll draw more of them next time. But anyway, my point anyway is that the composite of S with R and the composite of R with S both give us these what are called identity relations. In other words, the identity in A is S composed with R, and the identity in B is R composed with S. In fact, this example I just gave was an example of an inverse relation. So R and S are inverses. In fact, we can define that, right? So definition, given a relation from A to B, we define the inverse relation, R inverse, to be the relation from B to A, given by just flipping the components, basically, yx instead of xy. And theorem, the inverse relation of a relation is a relation. Moreover, the domain of R inverse is in fact the range of R, and the range of R inverse is the domain of R. The proof is there's really not much to prove here. These things, in fact, are immediate from the definition of R inverse. So anyway, the concept of an inverse relation is nice in that it avoids some rather cumbersome restrictions that come with the idea of an inverse function. All right, remember, inverse functions have to pass. They have to have that injectivity from a calculus perspective. Like you have to pass the vertical line test. To be a function, you have to pass the horizontal line test to have an inverse function. Relations, not so much, because we don't have that single valuedness. But anyway, I'm gonna go on here. An example. My example 2.5. So let's let S be x comma sine x. All right, such that make sure I'm in frame here. Such that x is a real number. This is a relation from the reals to the reals. And we can visualize it as the graph of the sine function, right? And the inverse would just be flip the sine and the x. And I used a y. Just if I was going to plot both S and its inverse in the same Cartesian plane, it would be useful to think of y in the y spot and x in the x spot, right? And if you were to graph these, the one would just be the usual sine graph like this, right? And the other one would be the sine graph like this. So it'd just be the same graph run upwards versus run sideways. But anyway, in fact, if you look carefully at the graph of inverse sine, you'll see it's just part of exactly that. More on that later when we talk about inverses of functions. Or not, actually. That's kind of more of a calculus question than in here. So, all right, theorem. A, B, C, D sets. Suppose R, S, and T are relations. R is a subset of A cross B. S is a subset of B cross C. T is a subset of C cross D. All right. In that case, we have following fun facts. The inverse of the inverse is the relation again. Composition of relations is associative. You can use the identity relations and just get back where you started again. And finally, the sock-shoes principle says that S composed with R inverse is R inverse composed with S inverse. So I would probably make these homework examples. We could probably prove one of these here in a second, but I'll just say a little bit more here. Item B says that we can compose T composed with S composed with R without ambiguity. In other words, the composite of relations is associative. And as I was saying, this is like the sock-shoes principle. If you think about it this way, if I put my socks on first and then I should put my shoes on second, right? Then when I take them off, the inverse, right? I have to first take off my shoes and then take off my socks. The other way around. So I don't know if any of you put your shoes on first and socks on second, but that would be odd, right? Let's see here. Trying to think. We could prove one of these. Well, I'll do the easy one, I suppose. I mean, this one is almost, the proof is almost laughable. So let R be a subset of A cross B, in other words, a relation, right? Then if we look at x comma y, an element of R, that is going to be true only if y comma x, right, is an element of our inverse by definition of inverse, right? And that is going to be true if and only if x comma y is an element of our inverse inverse, again by definition of inverse applied to our inverse itself, right? So we're thinking of our inverse as a relation. Because remember, we already noticed that the inverse of a relation is a relation in the previous page, and there you have it. So any element of R is also an element of our inverse inverse, which goes to show you that R is equal to R inverse inverse, which is what we set out to prove. Now the proofs of the other pieces here are similar. You know, you just pick an element in the left-hand side and just show it also has to be an element on the right-hand side. I'm gonna move on here for now. Let's see here. So up to now I've been talking about relations from one set to another, and those sets could be the same, but they didn't have to be, right? A and B could be different sets, but now we're going to focus our attention on relations on a set. So in this case we're taking the A and the B both to be equal to some set. Let's call it X. So if the relation is a subset of X cross X, then R is said to be a relation on X. Well, hold on a second there. Not so fast. Not so fast. What else do we need? This is kind of important. And what? The domain of the relation is equal to X. In other words, we're assigning an output to every input in this set X. Every element of the set X as a defined operation by the relation. Okay, so instead of writing A comma B as an element of R, we'll just write ARB. Or if A is not A, B is not in R, then we write A is not related to B. All right. So, by the way, at this point, I'm actually stealing some of these notes from my brother Bill, who's a professor of math at Appalachian State, and he had a handout on equivalence relations, which I thought was just right on point for what we're doing. So we're actually cut and paste this from one of his handouts, but just to give credit where credit is due, this is from Bill. So as Bill points out, relations in mathematics and regular life too, they're all over the place. I already gave you some silly examples, right? But we can also do other relations like brother or aunt or neighbors. Of course, we like less than or equal to or greater than or add to a rational number. Even subset of a set can be viewed as a relation. So let's see here. He said it is quite useful to abstract the concept of equality. Relations which behave like equals are called equivalence relations. We'll define those soon. And relations which behave like less than or equal to or subset are called partial orders. All right, so let me just get to it here, the name calling. So let R be a relation on a set X. It's said to be reflexive if X is related to X for all X. That's reflexive. It's said to be symmetric if X related to Y implies Y is related to X. It's unfortunate that the page did that there. I'm going to go ahead and write it on here again. Reflexive What's that mean? R is reflexive if and only if X is related to X for all X in the set in question, big X. It's symmetric. R is symmetric if and only if for all pairs x, y, and x, x related to y implies y is related to x, right? That's symmetric. It's antisymmetric if whenever you have x relates to y and y relates to x, that forces x equal to y. It's antisymmetric. It's transitive if x related to y and y related to z implies x related to z. And so we use those terms together to define an equivalence relation. An equivalence relation, R is an equivalence relation if it's reflexive, symmetric, and transitive. All right, that's definitely something I'd like you to memorize. And you should also understand carefully the meaning of those terms, reflexive, symmetric, and transitive. Okay? Partial order, X is partially ordered by R, or R is a partial order on X if R is reflexive, antisymmetric, and transitive. And then it's total or simple or linearly ordered if X is totally ordered. X is totally ordered by R, or simply or linearly ordered if and only if R is a partial order. And in addition, you have this sort of dichotomy that for any pair X and Y, either it's X is related to Y or Y is related to X. All right, so that's modeling. This idea of partial order or linear orders is really just a generalization of the notion of like less than or equal to or greater than or equal to. Apparently if we look at different books, there's a lot of different variations on the definitions for total. Well, there's variations on the notion of partial or total orders because some people try to capture inequality versus strict versus like they try to include the equals or don't include the equals, and just to say that this is a choice for this terminology, but there are other variations. But anyway, how about just regular old equality? Well, regular old equality on some fixed set is an equivalence relation. Let's see why. Suppose we have the real numbers, x and y, in the set, and other x and y real numbers. We'll define x related to y if and only if x equals y. So notice we got x equals x, right? What's that to say? That's to say reflexive. Sorry, I can't write that small. This guy is symmetric, right? And if x equals y and y equals z, then that means that x equals to z, right? So this is transitive. So plain old garden variety equality on the real numbers is an example of an equivalence relation. This is not surprising because really the notion of equivalence relation was modeled exactly on this. So just to, go back to some of my previous comments, if we look at the real numbers, we can define x related to y if and only if x is less than or equal to y. Is it symmetric? Is it reflexive? Is x related to x? Is x less than or equal to x? Well, yes, x is equal to x, so that makes that true, right? So it's reflexive. It's also antisymmetric, right? Because if we have x less than or equal to y and y less than or equal to x, that forces x to be equal to y. So R is antisymmetric. It's also transitive because x less than y, y less than z implies x is less than or equal to z. And of course, any pair, right, has either x less than or equal to y or y less than or equal to x, right? So in other words, less than or equal to is in fact a total ordering. again, this is not surprising because the whole concept of total ordering was modeled to abstract this notion. And now this is kind of a weirder example. At least it's foreign to my intuition personally. If we look at x, then the power set of x is partially ordered by subsets. This is usually read, it's partially ordered by inclusion. In other words, now the reason it's not a total order is because you can find subsets which are neither A is a subset of B nor B is a subset of A, right? If the picture looks like this, right? This is A and this is B. A is not a subset of B, B is not a subset of A, which means that if subset is the definition for the relation, right? Something being a subset of something else, then it's not going to give us a total ordering because this is, it's not one way or the other, right? And we need it to be one way or the other to get that total order. Here's some of the details on this. X is non-empty. He says define the relation to be A comma B, where A and B are subsets, right? This is just a fancy way to say that A comma B is a subset of the Cartesian product of the power set in itself. That's just saying that A and B are subsets, and this added condition says that A and B are disjoint subsets, right? So pairs of disjoint subsets. In other words, A is related to B if and only if A and B are disjoint subsets of X. So this relation is not reflexive because any subset is not disjoint from itself, and the relation is symmetric. It is symmetric though, since A and B are disjoint only if B and A are disjoint. It fails to be antisymmetric because just because A and B are disjoint does not mean that A is equal to B. This also fails to be transitive. So this is just basically an example where most of the terms fail. This is more of a logical, fun logical example to just kind of show us how these words can break down in a specific example. Okay, now I'm much more fond of the next example, rational numbers. Let me get a new sheet of paper over here. So rational numbers. What do I mean by that? So if we have our set is the integers cross the non-zero integers, then we can say A comma B, C comma D in this set are related if and only if AD is equal to BC. So I'll just tell you what what's the man behind the curtain here, so to speak, is that you can think of A comma B as basically being a model for, notice that the second component here is non-zero, so it's kind of like A over B basically. And the idea here is likewise, C over D is like, C comma D is basically modeling C over D. Right, so what does it take for two fractions to be equal? So if we've got A over B equal to C over D, then what we want from that is we want AD to equal to BC, right? So this is where this is coming from is the desire to model fractions in terms of characterizing their equality by cross multiplication. All right, but anyway, this is just a definition, so there it is. Now the question then is, okay, great, you got this definition for this, and you notice we're using squiggle here. So before we would have written like A comma B or C comma D, but usually as you go on, people start instead writing, we're instead writing A comma B, related to C comma D using the squiggle. So, or sim. Okay, so is it an equivalence relation? Well, yes it is, because AB is related to AB because AB is equal to BA. So it's reflexive. AB is related to CD. That means AD is equal to BC, but that also means then, of course, that CB is equal to DA, which is to show you that C comma D is related to A comma B, so it's symmetric. And also it's transitive. All right, so there's the argument for that. So this relates to that, gives me AD equals BC. This relates to that, gives me CF is related to DE. Multiply the first equation by F and the second equation by B, which we can do because they're both non-zero. And that gives us that ADF equals to BEF and that BCF is equal to BDE. But notice that this and that match up, which gives us the ADF equals to BDE, right? Or BED, right? And then since D is non-zero, you can cancel it off. That gives us AF is equal to BE, and that shows that A comma B is equivalent to E comma F. Therefore, squiggle is transitive. Now, this whole paragraph is, you know, if you translate it into fraction notation, it would be totally unsurprising. All right, maybe I should do that. Maybe I shouldn't. I don't know. I will hazard it. So, like, just to show you where these arguments are kind of coming from, we're saying suppose A over B is equal to C over D, right? And C over D is equal to E over F, right? But, so of course it implies that A over B is equal to E over F, right? But the paragraph is above, rather the paragraph above is what you have to work through in terms of the definition which is given, right? Because we don't get to use this equality, we have to go through the cross-multiplying definition for the equality of these two elements. But anyway, I'm going to not belabor this further. The point is that this is a careful way of logically constructing rational numbers. It's really, as he says, a relations, an encoding of the equality of fractions. And I mean, one thing you might notice here is, like, you could check this, but 1 comma 2 is equivalent to, you know, 2 comma 4 is equivalent to 3 comma 6 is equivalent to, I don't know, 100 comma 200. I mean, these are all different versions of the fact that 1/2 is equal to 2/4 is equal to 3/6 is equal to 100 over 200, right? All of these different fractions represent the same rational number, is the point. So that brings us to a definition here. If we have an equivalence relation, right, on X, then for each X in A, rather each A in X, we let the bracket A, close bracket, the set of all points which are equivalent, rather related to A, is the equivalence class of A. So here that is. So bracket A is the set of all elements of X which are related to A. We call bracket A bracket the equivalence class of A, and we say that A is a representative of this equivalence class. The set of all equivalence classes is often denoted X mod squiggle, right? So, like in this example, the equivalence class of 1 comma 2, it includes many things. It includes, of course, 1 comma 2. It also includes 2 comma 4. It also includes 3 comma 6. It includes infinitely many things, because all of these are different representatives of that single, they're all different versions, really, of the fraction 1/2. All right. They're all the same number, right? But these are different fractions, technically. All right. So, as Bill warns, there's no standard notation for equivalence classes. Another choice might be convenient for the equivalence relation R on X, like X mod R denotes the equivalence class containing X, and big X mod R is the set of all equivalence classes. Excuse me. Definition. So if we have a subset of the power set, in other words, a set of subsets, all right, then supposing that they're all non-empty, in other words, the empty set is not a subset of this P. And also, if we have that the union of sets in P covers X, right, then that means that for any point X in X, there's some A in P such that X is an element of A. And we also want to assume that if you pick any 2 points in any two subsets that are in this P, then they're either disjoint or they're equal. All right. So that means the distinct elements of P are disjoint. And anyway, in such a case, we say P is a partition of X. So a partition of a set is a collection of subsets which are disjoint and whose union covers the whole set. And they also have to be, I sometimes forget this, but the partition has to be formed by non-empty subsets. All right. So theorem. This is the most important theorem that I have in this lecture. Here it is. So the theorem says the following: let squiggle be a equivalence relation on X, then the set of then the equivalence classes of squiggle partition X. Conversely, given any partition P of X, you can define an equivalence relation, right, by saying that 2 points are related if and only if they're in the same equivalence. If they're in the 2 points are related, if and only if they are in the same member of the partition, right? In fact, then squiggle is an equivalence relation on X whose equivalence classes are precisely the elements of P. So the proof is given here. All right. Let's see if I see how it goes on to the next page. All right. The proof is right here. So we'll start. Make sure I have enough time left here. Yeah, we should be okay. So this is a biconditional proof, right? It's saying you can start with an equivalence relation and construct a partition, or vice versa. You can start with a partition and construct the corresponding equivalence relation. So he starts by saying, let it be an equivalence relation on X, right? So pick a point in X, right? Then since the equivalence relations are reflexive, that means A is related to A, right? Therefore, A is in the equivalence class of A, right? So what does that mean? That means that every equivalence class is non-empty. That's important because the partition has to be non-empty subsets, right? It also shows that every element of X belongs to some equivalence class. So that means that we've already shown that the equivalence classes cover the set X, right? So now all we have to do is to show that the equivalence classes are disjoint, right? So suppose you have A and B in X, and suppose that the equivalence class of A and the equivalence class of B is non-empty. What we need to show is that the equivalence class of A equals the equivalence class of B. All right, so since we've supposed that they're non-empty, right, it means that there's some C in their intersection, right? In other words, C is related to A and C is related to B. But that means what? By transitivity, well, so I'll tell you where we're going to go with this. Since C is related to A and C is related to B, by symmetry we have A is related to C, right? And then, since A is related to C and C is related to B, we'll get that A is related to B. Let's go on here. We'll see how he argues. So he says, since our relationship is symmetric, we also have that A is related to C. So A is related to C and C is related to B. So by transitivity, we have A relates to B, right? But that shows what? Also by symmetry, B is related to A, right? Okay. So now he's going to go about the business of showing that the equivalence class of A is equal to the equivalence class of B. In this paragraph right here, right, in this paragraph we just got done talking through, he's probably got all the data he needs to show that. Let's see how he uses that data in the next paragraph to prove the equality of the equivalence class of A and B. So suppose X is an element of A, equivalence class of A. That means X is related to A. Since X relates to A and A relates to B, that means that X relates to B by transitivity. Therefore, X is an element of the equivalence class containing B, represented by B. And what's that show? That shows that the equivalence class of A is a subset of the equivalence class of B. Well, that's great. That's half of what we need, right? Because we were trying to show these are equal. So by double containment, we need the other direction, right? So he basically is going to go through the same exact argument, except the opposite way. Pick X and B, the equivalence class generated by, represented by B. Then X relates to B. Remember, we already have B relates to A from up here. And so that means that by transitivity, X relates to A, which means that X is an element of the equivalence class containing A. And so B is a subset, equivalence class of B is a subset of the equivalence class of A. And so you notice what we've got the double containment, this guy and that guy, and so we get equality. All right, so at this point we have shown that given an equivalence relation, we get a partition because we get they're disjoint and they cover the set, and they're non-empty, right? So next order of business, the other way around, right? Suppose we've got a partition, right? Define A to be equivalent to B, A to be related to B, if and only if there exists some element of some set in the partition such that A and B are in that set. All right? So here's how this goes. First, we'll let A be an X. Since P is a partition, that means there has to exist some A in the partition such that A is an A. Thus, A and A are both in A, which means that A relates to A. So our relation is reflexive, right? Next, if we suppose A is related to B, then that means there has to exist some E in the partition such that A and B are both in the partition. A or B are both in E, but that means, of course, that B and A are both in E also. So B is related to A. So that means our relation is symmetric. If we have A relates to B and B relates to C, that means that we've got something in the partition E and E prime such that A and B are in E, and B and C are in E prime, right? But that means that B is both in E and E prime, right? That means that B is in the intersection of E and E prime. So that must mean that E intersect E prime is not the empty set. But distinct partitions are disjoint, right? Which means then that these must not be disjoint. In fact, they have to be equal by our definition of partition. So thus E equals E prime, which means that A and B and C are all in E, which is equal to E prime, which is to say that A and C are both in E, which goes to show that A is related to C, which proves then, remember up here we assumed that A relates to B and B relates to C. We've just gone through what it takes to show that A is related to C, which establishes the transitivity of the relation. So, what else? So if E is in the partition, then E is not empty. So there exists some A that's in E. And so we also can notice that X is in E implies that A and X are in E, which implies that X relates to A. So X is an element of the equivalence class with A in it, and that means that E is a subset of A because we've picked X. Notice that we picked X in E, right? We picked X in E, and we just showed that X was an element of here, which shows you that this inclusion is the case, right? E is a subset of A. And now he's going to go the other way around. He's going to suppose x is an element of the equivalence class with a in it. That means x related to a, so there exists some e prime. We can't assume it's the same one just yet, e prime and p, such that a and x are in e prime. But then notice that a is also in e, right? So a is in the intersection of e and e prime, which forces e to be equal to e prime. Consequently, ax is in e, which is also in e prime. So in particular, x is in e. So you notice what's happened here. He's started by picking x and suppose that x is in a, and we have gone through arguments that show that x is in e, right, which gives us that the equivalence class of a is a subset of e. But when you put that and that together, you have double containment, so the equivalence class is in fact equal to the partition. And so what we've just shown is that anything in the partition is in fact matching the equivalence class of the relation which we've defined, and that was the claim of the theorem. So I hope you can understand that proof. If you didn't understand it the first time, think through it for yourself. It's really not a particularly difficult proof, but it involves a lot of steps. And it's easy to forget something in that, but all those steps are needed to prove the claim of the theorem. So one last hurrah, if you will, for this lecture here. It'll be done. Suppose that we have s as the integers, and we can define x, y, and integers to be related if their difference is even. So this is just a fancy way of saying the integers even are related to even and odd are related to odd. All right. Is that an equivalence relation? Well, yeah, it's reflexive because x minus x, which is 0, which is even for any integer x, right? If x and y are integers and x relates to y, that means x minus y is 2k, but that means that, y minus x is minus 2k, which is 2 times minus k, which means that y relates to x, so we've got it symmetric. To get transitive, if we've got x relates to y, y relates to z, then we've got an m and a k such that x minus y is 2k and y minus z is 2m. So if you do this little calculation right here, x minus z is, I just add and subtract y, x minus y, y minus z, like that. And the reason I do that is simple. It's because I've got data about x minus y, and I've got data about, because I know that this, right? And I've got, y minus z. I know from what's given that y minus z is 2m, right? So I want to put that there. So that gives me the 2k and the 2m. And so factoring that out, I've got 2 times k plus m. But of course, if k and m are integers, then k plus m is also an integer, which shows that x minus z is even. And so we've also shown that x relates to z, which shows that it's transitive. In total, we can conclude that R is an equivalence relation on z, since, and in fact, it's perhaps interesting to look at the equivalence classes here in this case. The equivalence classes, where there are just 2 of them. The one is the even integers, and the other one is the odd integers. I would just point out that you can continue this example to look at things being equivalent if they differ by like a multiple of n. And if you look at that equivalence and you partition the integer into like multiples of n, and you'll get n of them. Like we looked at multiples of 2, we got 2 equivalence classes. If you looked at multiples of 4, you get 4 equivalence classes. If you did the same idea with multiples of 5, you get 5 equivalence classes. Anyway, this leads you to the notion of modular integers. And in fact, these have been used since the time of Gauss to unravel difficult questions in number theory. But I don't expect we're really going to need those for this course, so I just mention it as a point of trivia for you. Certainly if you go on to take abstract algebra or number theory, you will see much more about modular integers. I just mention it here because it's really part of this story. So anyway, next time we will move on to functions, which will perhaps be more familiar to you, and we'll talk about what it takes for a function to be a bijection, and so forth. So thank you.